All right, so in this video, we are going to talk about series. First of all, I'm going to write out what a series would be. So series are going to be infinite sums. So maybe we have sum from n equals 1 to infinity of a sub n. And what this means is we are summing up an, and we're plugging in each index. So I have a1 plus a2 plus a3, and I add all the way up to an, and I'm going to keep on going because I'm adding infinitely many things. So this is what a series is. It's an infinite sum. And so if we say that a series is convergent, so we say the series is convergent if this sum tends to a finite value, otherwise, the series is divergent. Okay. And so we can look at a couple divergent series just to kind of get a hang of what's going on. Let's say I take the sum n equals 1 to infinity of, let's just say I'm summing up a number, so 2. Well, if I write out what this means, this is going to be 2. This is going to be 2 plus 2 plus 2 plus all of my a sub n's are 2's. And I'm just going to keep on adding those 2's together. So I'll have 2, 4, 6, 8, and I'm adding those up. And so this series, this sum is obviously not tending towards a finite number. This is going to go to infinity. We could look at something like n equals 1 to infinity of, let's say, negative 1 to the n. This is equal to negative 1 plus 1 minus 1 plus 1 minus 1 plus, and we're going to keep on going. And looking at this, you might initially think that this sum is going to be equal to 0, because if you look at two consecutive terms, they would end up zeroing out. But here's where we want to see where this sum is tending to. And so this gives motivation into looking at the sequence of partial sums. So when I say the sequence of partial sums, we're going to look at, so up here, I'm going to define Sn to be a sub 1 plus, and I'm just going to add up to a sub n. That's going to be my partial sums. And I'm going to look at what happens to the sequence of my partial sums. So I'll write out S1 is equal to a negative 1. S2 is negative 1 plus 1, which is 0. S3 is negative 1 plus 1 minus 1, which is a negative 1. S4 is a negative 1 plus 1 minus 1 plus 1, which gives us 0 again. And we're going to keep on going. And so Sn is equal to, and we have this pattern established where it's negative 1 if n is odd, and we have 0 if n is even. And so if we're asking what's happening to the sequence of partial sums, so we're considering the sequence negative 1, 0, negative 1, 0, on and on and on. And we were to ask, does this sequence converge or diverge? You would say that this sequence diverges because it's not actually approaching a number. It's just oscillating between negative 1 and 0, and it's never actually approaching a finite number. And so we say that limit as n goes to infinity, nth partial sum, that this limit does not exist. So when we're talking about the series n equals 1 to infinity of a sub n, we're going to say that this series is divergent. And so coming back up here, we defined our partial sum, our nth partial sum. And when we're trying to look at what the sum of the series is, we're going to write that the sum of the series, n equals 1 to infinity of a sub n, is going to be equal to limit as n goes to infinity of s sub n, if the limit exists. So that's how we're going to find our infinite sum, or the sum of our series, is we look at the limit as n goes to infinity of our nth partial sum, or what happens to our sequence of partial sums. All right, we're going to do another example. Let's say we had the sum n equals 1 to infinity of 1 over n times n plus 1. And so looking at this, it might not be obvious where this series is going to be tending to as we continually add 1 over n times n plus 1, and we keep adding those. It might not be obvious where this is going. So instead, we're going to look at the sequence of partial sums. So I'm going to look at S1 being 1 over 1 times 2, or 1/2. S sub 2 is going to be 1/2 plus 1 over 2 times 3, or 1/2 plus 1/6, which simplifies to 2/3. I can look at S3, which is 2/3, my previous partial sum, plus the next term I would add, 1 over 3 times 4, which ends up giving me a 3/4 when I simplify. S4 is going to be 3/4 plus 1 over 4 times 5. And this, when you add and simplify, is going to give you 4/5. And we could keep going. Well, if you look at the sequence of partial sums, I'll write them out. So far we have 1/2, 2/3, 3/4, 4/5. We can see the pattern that our S sub n is going to be equal to n divided by n plus 1. So that's the pattern of our partial sum. So for example, if I wanted to figure out the sum of the first 100 terms, I know that it's going to look like 100 over 101. And so when we're evaluating what's happening with this series, we're going to look at limit as n goes to infinity of s sub n, or n over n plus 1. Well, this is a limit that we can evaluate rather easily and get 1. And so that's going to be our sum. All right, for our next example, we're going to look at the series n equals 1 to infinity of, let's say, 1/2 to the n minus 1. And so we're going to play the same game. You might look at this and think, okay, I'm not quite sure when you're adding these where it's going to go. So we're going to look at the sequence of partial sums. We'll look at S1, S2, S3, and we'll try to come up with a general formula for Sn. And then we'll take the limit as n goes to infinity of Sn. So real quick, I'm just going to write out what this series is looking for. So when I plug in n equals 1, I'm going to get 1/2 to the 0, so 1. My second term is 1/2. My third term is 1/4. My fifth term is 1/8. And I keep on adding, just like that. And so my first partial sum is going to be 1. My second partial sum is going to be 1 plus 1/2, or 3/2. My third partial sum is going to be 3/2 plus 1/4, or 7/4. And maybe we need a couple more terms to establish a pattern for S sub n. So let's do S4 is going to end up giving us 15/8. And so we can look at what's happening with our sequence of partial sums and find that our general formula for S sub n, in our denominator we have 1, 2, 4, 8, so on and so forth. So it's going to be 2 to the n minus 1. And up in the numerator, we have 1, 3, 7, 15. If we think about 2, 4, 8, 16, that looks like 2 to the n, and then we're just subtracting 1. And so when we're evaluating the sum, we're going to look at the limit as n goes to infinity of 2 to the n minus 1 over 2 to the n minus 1. And we can rearrange this a little bit and get 2 times 2 to the n minus 1 over 2 to the n. And when we evaluate this limit, we end up getting a 2. And so the sum of this series is going to be equal to 2, which actually kind of makes sense. If we sketch out a number line real quick and try to kind of fill in what's happening with this sum, the first thing that I'm adding is 1. So let's say this is 0, 1, and then 2. I'm first adding a 1. So I'm adding from 0 all the way to 1. And then I'm adding 1/2 to that. So from 1 to 2, I'm taking 1/2, and this is what I'm adding. And then I'm adding 1/4, which is actually half of what's remaining. And then I'm adding 1/8, which is again half of what's remaining. And then with each time that we're adding something, we're going to add half of what's remaining. We'll add half of what's remaining, and we could zoom in there, and there would still be a bunch of space. That then we would add half of what's remaining, half of what's remaining, half of what's remaining. And so our sum is going to approach 2, but it's never going to surpass 2 because we're always adding half of what's remaining between where we are and 2. And this theorem is going to be called the test for divergence. And it states that if the limit as n goes to infinity of a sub n, the terms that we're adding in our series, if that is not equal to 0, then our series must diverge. And that's based on the same intuition that we had previously, that if we know that the series is convergent, then the sequence of our terms must go to 0. And this theorem is saying if the sequence of our terms that we're adding does not go to 0, then our series can't converge. It must diverge. So we'll use this in an example problem real quick. Let's suppose we're looking at the series n equals 1 to infinity of, let's say, n squared minus 5n over natural log of n plus 1. And we're looking at this series and we're trying to determine if it diverges. Well, if we look at the limit as n goes to infinity of n squared minus 5n, all divided by natural log of n plus 1, which are the things that we're adding, as n grows to infinity, this quotient also goes to infinity. So that means that we are adding, as we continue adding these terms, we're adding larger and larger numbers. So then, of course, this series can't converge. So we can say by the test for divergence, you can write TFD, the series converges. No, diverges. The series diverges. All right, now we're going to look at a couple different series and sum different techniques that you can use to find the sum. So let's start off with n equals 1 to infinity of, let's say, natural log of 5n plus 5 minus natural log of 5n plus 10. Now, if you look at the limit as n goes to infinity of the terms in our sequence, we have natural log 5n plus 5 minus natural log 5n plus 10. You may try to see where this goes. Well, we can use some algebra and say that this is equal to the limit as n goes to infinity of natural log of 5n plus 5 divided by 5n plus 10. And when we evaluate this limit on the interior, the 5n plus 5 over 5n plus 10 as n goes to infinity ends up approaching 1. So this limit ends up going to 0. And so then you should ask yourself, can I make any conclusions based off of this? Can I conclude that this series is convergent because the things that I'm adding up go to 0? And the answer is actually no. If you find out that the limit of our a sub n's, when we're looking at the series for a sub n's, if you find out that that is equal to 0, you can't actually conclude that if it's convergent or divergent. And so you might ask, well, how the heck are you supposed to deal with this series? And this series actually ends up being a telescoping series. And by that, I mean that if you write out what the series is, you're going to get a bunch of cancellation of the terms. So let's go ahead and do that so you can see what I'm talking about. We would have sum n equals 1 to infinity of the natural log of 5n plus 5 minus the natural log of 5n plus 10. And so let's just write out term for term what this is talking about. We have natural log of 5 times 1 plus 5 gives me 10, minus natural log of 5 times 1 plus 10 gives me 15. That's my first term. That's a1 plus. My a2 is going to come out to natural log of 15 minus natural log of 20. My third term, a3, is going to come out to natural log of 20 minus natural log of 25. And I'm going to keep going. And eventually I'm going to hit natural log of 5n plus 5 minus natural log 5n plus 10. And then I'm going to keep going because it's an infinite sum. Well, you might notice that there is quite a bit of cancellation here. If my natural log of 15 from a1 cancels with the natural log of 15 from a2. The natural log of 20 from a2 cancels with the natural log of 20 from a3. If this pattern continues, the natural log of 25 is going to end up canceling. And then this natural log of 5n plus 5 is going to end up canceling. And we'll continue having cancellation all throughout this series. And so we might not be able to right here say what our series is equal to, but we can surely write out what our nth partial sum is going to be. It would end up being natural log of 10 minus natural log of 5n plus 10. That's our nth partial sum. And here we can take the limit as n goes to infinity of our nth partial sum. Well, as we take limit as n goes to infinity, natural log of 10 stays natural log of 10, and then we end up subtracting natural log of something that's going to positive infinity, so we end up getting negative infinity. So that's where our nth partial sum is going as n goes to infinity, which lets us know that this series, I'm just going to write a sub n, that this is tending to negative infinity. So it's divergent. Even though if we look at what's happening to our terms here, right here, even though our terms are going to 0, our sum is still going to negative infinity. All right, we will do another example. So we have the sum n equals 1 to infinity of, we're going to do actually the same example that we wrote out the partial sums for, but I want to show you how this ends up being a telescoping sum, actually. Now, we've learned about partial fraction decomposition. If you do the partial fraction decomposition for 1 over n times n plus 1, you'll end up getting that you can rewrite this as 1 over n minus 1 over n plus 1. Well, in this form, I can write out term for term what's going on with my sum, and we'll actually see some cancellation because we have it written as a difference. So a1 gives me 1 over 1 minus 1 over 2. A2 gives me 1 over 2 minus 1 over 3. A3 gives me 1 over 3 minus 1 over 4. And we're going to keep summing. And eventually we'll have 1 over n minus 1 over n plus 1. And since we're dealing with an infinite sum, this would continue going. Well, we can see quite a bit of cancellation. The 1/2 cancel, the 1/3 cancel, the 1/4 would cancel with the next term. The 1 over n would cancel with the previous term, and so our nth partial sum, s sub n, is going to be equal to 1 minus 1 over n plus 1. Well, now we have this partial sum written out, and we can take a limit as n goes to infinity of 1 minus 1 over n plus 1. And we end up getting that this is 1, the same answer that we got before, just using a different method, seeing this as a telescoping sum instead of looking at the s sub 1, s sub 2, s sub 3, and coming up with a general formula for s sub n. So, again, to kind of hammer it in, this example we solved by looking at this as a telescoping sum, and the previous example was also a telescoping sum. All right, so that's a special type of series where this very special thing happens, where if we write out all of the terms, well, not all of the terms because we have infinitely many. If we write out a lot of the terms, we will see that we have this really nice cancellation that then allows us to find our s sub n in this really nice form that we can evaluate the limit. All right. Now we're going to talk about what are called geometric series. And these result from summing up geometric sequences. So remember, a geometric sequence was something like maybe we had 2 and then 2/3, so I'm multiplying by 1/3, and then 2/9, and then 2/27, and we keep on going. That would be a geometric sequence. A geometric series would be if we were to look at 2 plus 2/3 plus 2/9 plus 2 over 27, and we were to continue to sum that up. Well, we can describe our geometric sequences as so this one could be described as 2 times 1/3 to the n minus 1. And so our geometric series can be described as the sum, n equals 1 to infinity of, this one would be 2 times 1/3 to the n minus 1. So the consistent thing that we'll have with geometric series is that we'll have the sum from n equals 1 to infinity of sum a times our common ratio raised to the n minus 1. And if you recall, we had these index shifts where instead of starting at n equals 1, maybe we started at n equals 0. And so we can rewrite this where we'll have a times r to the n instead of the n minus 1. So both of these are equivalent. We're just shifting the index a little. And so we can actually find the sum of these geometric series, and we can actually determine the formula for the sum for any geometric series. And so to do that, we're going to write out what the nth partial sum is. So if I look at S sub n, that's going to give me a plus a times r plus a times r squared plus a times r cubed. And we'll keep on adding until we get to a times r to the n. That would be our nth partial sum. And I'm going to multiply this equation by r. So I'll multiply by an r. I have s sub n. And on the right-hand side, I have a times r now. I have a times r squared. I have a times r cubed. A times r to the 4th. All the way up to a times r to the n plus 1 now. And I'm going to go ahead and subtract these equations. When we subtract, we end up getting 1 minus r times the nth partial sum is equal to, and here we don't have a telescoping series because we're not looking at a telescoping series, but we get a lot of really nice cancellation like it. So our a sub r, we're subtracting, keep in mind we're subtracting here, and a sub r. Our ar squared cancels with our ar squared. Ar cubed cancels with our ar cubed. And we're going to continue canceling everything except for our a and our plus a r to the n plus 1. And now here we can actually write what our nth partial sum is going to be. We have a plus a times r to the n plus 1 divided by 1 minus r. Now given r is not equal to 1. If r were equal to 1, our denominator would be 0. So we're excluding that case here. And now we can look at what happens to limit as n goes to infinity of our s sub n, or a. I'm going to factor the a out. We have 1 plus r to the n plus 1 divided by 1 minus r. Well, here, if we take n to infinity, one of two things is going to happen, and it's all dependent on this r to the n plus 1. If the absolute value of r is less than 1, so if r is something like 1/2, 1/5, negative 1/3, something like that, the r to the n plus 1 as n goes to infinity, this is going to tend to 0. If we have something less than the absolute value of r less than 1, we'll end up finding that this limit is equal to a over 1 minus r. If the absolute value of r is greater than 1, then this r to the n plus 1, if r is something like 5, this is going to end up going to infinity. If r is something like negative 5, this is going to end up jumping around everywhere. We'll have, if we have n is even, we'll have a negative growing number. If n is odd, we'll have a positive growing number, and that's because of this plus 1 as well. And so we'll end up getting that this limit, I'm just going to write does not exist. It could be infinity, it could be does not exist. We don't know. And then if we look at the case when r is equal to 1, we would be looking at this series n equals 1 to infinity of a times r to the n minus 1. Well, this is just, if r is 1, we just have a times essentially 1. So we have n equals 1 to infinity of a, which is just a plus, and we add that up multiple times. And so this clearly would go to infinity, or possibly negative infinity if a is a negative number. And so this one is divergent. So here we have convergent for absolute value of r less than 1, and we have divergent for absolute value of r greater than 1, or if r is equal to 1. So to summarize, we have a geometric series is convergent for absolute value of r less than 1 and divergent otherwise if we have that absolute value of r is less than 1, then we can actually find our sum. We have sum from n equals 1 to infinity of a times r to the n minus 1 is going to be equal to a over 1 minus r. So we can actually find exactly what our sum is equal to. So for example, we could be looking at the sum n equals 1 to infinity of 5 times, let's say, 4/7 to the n minus 1. This is a geometric series. We have it set up as sum n equals 1 to infinity of a times r to the n minus 1. Our a is 5, our r is 4/7. We have that the absolute value of 4/7 is less than 1, so this is going to be convergent. And in fact, it's going to be equal to a divided by 1 minus r. So our a is 5 divided by our r is 4/7. So we've got 5 divided by 3/7, or 35 over 3. That would be our sum. If we had something like n equals 1 to infinity, maybe we have 4 times -6 to the n minus 1, we can see that the absolute value of r is greater than 1, so our series is going to be divergent. And we don't actually really have to do any more work than that. Just point out that absolute value of r is greater than 1. And it could be greater than or equal to 1. If it were equal to 1, it would still be divergent. You might get some examples where you kind of have to do some manipulation before you can actually figure out what the sum is, or if it's convergent or divergent. So say we have n equals 1 to infinity of, let's say we have 3 to the n plus 1 times 1/5 to the n. Yeah, let's do that one. Well, we have to rearrange this into the form, or see if we can rearrange it into the form of a geometric series. So that would be sum n equals 1 to infinity of a times r to the n minus 1. So what I would suggest that you do is get any number that has an exponent to it. I would shift it to where it is n minus 1 and pull out factors as needed to get them to n minus 1. So for instance, this 3 to the n plus 1. If I pull out a factor of 9, I would end up having 3 times 3 times 3 to the n minus 1. So now I have that exponent to the n minus 1. If I pull out a factor of 1/5 of this 1/5 to the n, I would then be left over with a 1/5 to the n minus 1. Now at this point, I have the same exponent. I can multiply the bases together using properties of exponents. And I would end up getting 9/5 times 3/5 to the n minus 1. Now at this point, I can identify that my a is 9/5 and my r is 3/5. 3/5 for sure is within the required bounds to be convergent, so absolute value of 3/5 is less than 1. So we have that this series is going to be convergent. To find what the sum is equal to, I can write S is equal to, my A is 9/5 and 1 minus my R is 3/5. So I'd have 9/5 divided by 2/5, which is equal to 9/2. And that would be my sum of this geometric series.